our trained data here, going down the road of doing time series analysis, specifically what we're going to do is classical decomposition. And what I'm doing here is following a textbook, which I really highly recommend, called Forecasting Principles in Practice, 3rd edition, written by a professor at Monash University, or two professors, who are very good in math, of course, and statistics, and also strong programmers. They wrote the packages that accompany this book, so it's really a really great resource. Now, in order to get started, what we're going to do is we're going to go through the packages that they have, the T-Sybil package and other ones, but also we're going to explore how to do classical time series decomposition ourselves. So the first thing you do is you load library, of course, but then also FPP3, which is a package that includes, for example, feasts and T-Sybil and other feasts for time series graphic and T-Sybil for using Tibbles like time series objects. And it also comes with data, for example, U.S. employment, which we can see is a T-Sybil object with a unique index, but it also has a key, so it's like multiple time series in one. What we're going to do first is actually just turn that into U.S. retail employment, and this is code lifted directly out of his book in order to make it a more simple index. And then what we can do is auto-plot it. Auto-plot is like ggplot, but it doesn't need to take an argument for the x because it understands the index of the T-Sybil. So you really just feed it the data and then the y. And here we have our time series. Now, time series decomposition. Decomposition is a word you might recognize if you are versed in linear algebra, doing something like eigen decomposition or singular value decomposition. Or if you've worked with like Fourier transforms where you need to find a signal, that's also like a decomposition. But you can also do time series decomposition. We see that this data has a trend, by which I mean it goes up. There may also be a cycle. Cycles are longer than trends. They go through periods at a regular interval, like car sales have been known to be on a 7-year cycle. The seasonal period, we see that there are like 30 spikes here because there are seasonal periods every year, and this is 30 years worth of data. And employment or unemployment increases in the summer or the winter. And then also there's the white noise remainder error component that's left over. So in order to do decomposition, what we do is we specify the model, classical decomposition, the y, the employed, specify the type as additive, and then we call on the components. And we can see the components being the trend, the seasonal, the random, the seasonal adjusted versions. And then we can auto-plot it. And auto-plot creates this beautiful plot where we have our original series on the top, we have the trend cycle underneath it, the seasonal period, and the remainder component. In classical decomposition, the trend cycle is cut off a little bit at the beginning and the end, because it doesn't come up with values on the tails. It's just a feature of classical decomposition that's been accounted for in the more robust version STL decomposition, which goes through the data twice. So how do we do that? How do we know? And here is a math equation for the remainder component. Remainder is equal to the data y at time t subtracted from the calculated trend cycle at time t and the calculated seasonal period at time t. If you're interested in being able to put math equations within your RStudio, you could specify them within the $, and then the alignment is very useful, the beginning and the end. And finally, you can specify x equals y, or whatever your math equation is. Here, if you use an underscore, it's going to create a subscript, and if you use a \hat, it's going to create a hat for t or a hat for y. So these are a useful way to keep your R console nice. Now, I've already written out much of the code for time series decomposition here. So U.S. retail employment, what you might want to do to create the trend cycle is use the slider package. So I'll build it from the bottom up so you can see. Skip ahead in the video if you want to do all this yourself. But U.S. retail, employment. What you first do is you want to calculate the trend cycle. If, for example, you're doing a trend cycle with a 7 moving average, the slider package, by the way, with the slide double function is extremely useful for being able to create a moving average. What you do is you feed it the y that you're creating a moving average of. The function, it could mean is most likely, but you could also do something else like median. Specify dot before equals 3, dot after equals 3, and dot complete equals true. So this would work if the data had a weekly seasonality. This would be smoothing for data with a weekly seasonality. However, we have a 12 MA and 6 doesn't work so well. 6, 5, like what do you do? Because if you do 6, 6, it's going to take a moving average that isn't symmetric. And you want it to be symmetric. So what you could do instead is take a moving average of a moving average. And the notation is you do 2 by or 3 by, but we're going to say 2 by 12 MA to do a moving average of a moving average. Switch this to 0 and 1. Add these up, 6, 5, 1 equals 12. And here we're creating a moving average of a moving average. A moving average of a moving average is going to be equivalent to a weighted moving average because the observations don't come in with full weight and they don't leave with full weight, and so it's actually more smoothing. The next thing we want to do is calculate the detrended data. The detrended data is, and I'm going to specify this as trend cycle, just so we're clear. You take the data and you subtract the trend cycle to get a detrended version of the data. And the next step you want to do in order to calculate the value of the seasonal periods is you have to calculate the average of the detrended data for each seasonal period. Now there isn't an index here that's super clear for how to group by because each one's unique. So we're going to have to do a little bit of work to say, for example, as date on month, and then for example, calendar month is going to be, you format that date %m as a month. Run this line of code so far, missing a comma. As date, let's run the line of code like here, as date month. Misspelled format. So here we have the date, here we have the calendar month. If we wanted to, for example, turn these calendar months into names that you recognize, I mean, you recognize these names, but you know, something maybe more common. You could use a case when statement when case when of the calendar month is double equal to 0, 1. We put that in quotation marks because it's a character data type, and do a tilde to make January, comma, copy and paste all the way down. Oops, going a little too fast. Feb, bear with me, March, April, May, June, July, August, September, October, November, December, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. And now, because it's a T-Sybil and it already has a grouping, I'm going to convert it to a Tibble and ungroup it. And now I can group by the month name and then summarize. The seasonal period is going to be the average of the detrended data for each seasonal period. And I'm going to do na.rm equals true. But at the same time, I'm also, because classical decomposition doesn't get it at the ends, I'm going to filter it cannot be is NA detrended. And now I'll save it as a data frame called seasonal period. And I could put a parenthesis at the end and a parenthesis at the beginning. And that lets me run the line of code while also printing it to the console. Now, if I copy all of this code before the group by, I can now inner join my new data frame on seasonal period by equals seasonal period, by equals month name. And finally, I want to calculate the remainder component. Remainder is equal to the employed minus my trend cycle, wrap that in backticks, minus the seasonal period. And here, assuming there are no errors, I have reconstructed, well, let's do one final step, which is I'm going to select just the variables I'm interested in to make it like the same. Employed detrended seasonal period and remainder. Okay, now my new data frame here has the original data. It has the trend cycle, the detrended version from it, which is the data minus the trend cycle, the seasonal period, which is the average of the detrended data for every seasonal period, and the remainder that's left over. And so this is my classical decomposition, reconstructed according to the logic of how it's done. Now, classical decomposition is really useful because what you can do is you can start to understand the time series components. You can see what is an outlying observation because it will be unusual within the random component. You can also create seasonal adjusted version of the data, which is really useful for economists, for example, who want to understand the underlying state of the economy while accounting for seasonal effects. You can also do forecasting models, like non-seasonal forecasting models on seasonal adjusted version of the data. So this is extremely useful. So here, for example, what I'm doing is I am taking the code that's directly from the textbook, and I'm creating seasonal adjusted version of the data. This shows the underlying trend while accounting for the seasonal effects. I hope this was helpful in understanding the math behind classical decomposition. And let's do one final thing, actually. Decomp, components of the decomp. Yep. And then what I would want to do is also geom histogram the remainder component. Geom histogram remainder. Well, shoot. Let's see. Decomp. Let's save that as a object. Decomp. Oh, that's a model. I see. So I'm going to save that as a tibble. And now I'm going to ggplot as the aesthetic the remainder component with, for example, a geom histogram. I just want to show one final thing. So in the seasonal decomposition, the remainder component should follow a normal distribution. So any outlying observations that are plus or minus 2 or 3 standard deviations away from the center of that distribution are going to correspondingly have a very low p-value.